All right, so we're going to take a look at 145, number 12. So let's read the question here. So it says, determine the area of the largest rectangle that can be inscribed in a right triangle if the legs adjacent to the right angle triangle are 5 and 12 centimeters long. The two sides of the rectangle lie along the legs. Okay. Then it says repeat part A for a right angle triangle that has sides 8 and 15. Okay. And then presumably there's some sort of pattern, and we'll see if we can find that. All right. So,
Sorry.
yep.
I asked for question number 20, not 12.
Oh, sorry, I was looking at the wrong one. Okay, well, there we go. Let's take a look at this one here. Number 20, this one here, determine the minimal distance between this point and the given curve.
Yeah, that's it.
Okay, perfect, thanks, sorry about that. All right, so this is page, is it? Page 147, number 20. Okay, and this is gonna be, should be fairly similar to the one we saw in class. I'm just going to write everything out. So here we want the minimum distance, and that's from -3 to y equals x minus 3 squared. All right. So again, as I usually do, I'm going to draw myself a diagram here to see what this looks like. Now, first thing I want to keep in mind here is that -3 is not on this curve. Okay, if you stick in -3, you don't get 3. Okay, so just keep in mind that we're dealing with a point that's outside of the curve. So here, x minus 3 squared, so it's just x squared moved to the right by 3 units. Okay. And then we have -3 somewhere there, and we want to find the minimum distance. Okay. Now, anybody want to make a suggestion as to what else I'm going to add onto this diagram to help me out, to help set it up?
Well, you know that the point that it hits on the curve is x, and then x minus 3 squared is the y value of it.
There you go. So what I want, so I've got this point, -3, okay, and I'm looking to find the shortest distance to some point on this curve. I don't know that point, so I can call it xy, but I can do one better than that because I know that the point is on the curve, meaning the y value is just given by x minus 3 squared. Okay, so in a sense, we've already done a substitution like we often have to do when we're finding a model for this here. Okay, so now we have our distance formula. Now, normally I would be writing my distance formula using a square root, but now that we have implicit differentiation, I'm actually not even going to go that route. I think what I might do is I might just leave Pythagoras as is, so I know this distance squared that I'm trying to minimize, okay, is just the difference of the x's squared. So x minus -3, so x plus 3 squared, and then the difference of the y's squared. Okay, so here what do we have? Let's be careful here. We've got x minus 3 squared minus 3, okay, and that's squared. All right. And so what I'm going to do here is I'm just going to differentiate this using implicit differentiation instead of taking a square root and having to deal with that that ugly square root when I'm taking the derivative. Not that it's a big deal, but you know, now that we have something that makes things a little nicer, we might as well use it. All right. So now what I'm going to do is I'm going to take, I'm not going to write it all out. I'll just say I'm going to take dx of both sides. Now, by the way, what is something that I should have been explicit about when I wrote my model? What's missing? What else should I be including anytime I have a model that I'm trying to optimize?
It's
Yeah.
Positive.
Yeah, the domain. Okay. So is there any restrictions on what x can be here? And I say, well, x can be anything because it could be any point on this curve that is the closest one to negative 3, 3. Okay, so this is one of those few scenarios where we actually have, the fact that x can be any real number. All right. So let me take the derivative with respect to both sides. And so here there's going to be a lot of chain rule. So if I'm taking the derivative of this with respect to x, first I take the derivative of the outside function, which is going to be 2d, and then I'm taking the derivative of d with respect to x. All right. And this is going to be the thing that I'm going to want to, make equal to 0 later on. Okay, so here again, instead of multiplying everything out, I think I'm going to just see if I can get away with, again, using the chain rule. So here, if I take the derivative of this, it's just going to be 2 times x plus 3 times the derivative of x plus 3, which is 1. Now, you might sort of say, why even bother writing that? It's just to kind of keep yourself thinking that I'm actually applying the chain rule here. All right, and plus, so this is going to be 2 times. Now, at this point here, I think I am going to have to expand this expression. I don't think I have any choice but to expand that expression. So I might as well do that now. So x squared minus 6x plus 9. And then, of course, I've got the minus 3. Okay. And now I have to multiply this by the derivative of the inside function. Okay. Now I know that the derivative of 3 is just going to be 0, so I'm taking the derivative of this thing here. So it's just going to be 2 times x minus 3 times the derivative of x minus 3 is just 1. Okay? So everybody okay with the derivative that I just took? Does anybody have any questions about this derivative? Okay, ask now. Make sure you understand everything that I did.
Sorry, I'm just a little bit confused about why can you use implicit differentiation here? Like what value are you going to sub in?
So implicit differentiation can be used anytime that you have a function defined implicitly. So there's no condition as to when you use it. So because I've got d that's defined where the d is squared, it's sort of one of the components of this equation. So I can use implicit differentiation in any scenario. There's no condition under which I can use it, okay? I'm using it here because it allows me to sidestep having to work with a big square root, okay? Now, remember what we're looking for is we're looking for optimal values. Where are we going to look for those optimal values? We're going to look for where the derivative is equal to 0, okay? So I guess the first thing, if I want to, kind of do things stepwise processes, I'm going to isolate dx, and then I'm going to set it equal to 0 because I'm looking for my, what am I saying? I'm looking for my critical points, all right? So can you see something real quick I can do to just simplify this equation a little? Just kind of helps to get rid of something right off the bat. Yeah, there we go. I can divide both sides by 2. So that 2 will go, and then these 2 here. So just divide both sides by 2. I might as well make my life a little simpler, okay? So my goal is to, isolate this derivative. So let's start simplifying. So if you can please keep an eye on my algebra here. So here I'm just left with x plus 3. That's nice and easy. Okay, plus. Now let's see what we're left with here. So I'm going to take my time and write this out carefully here. X squared minus 6x, 9 minus 3 is 6, and I'm multiplying that by, so this 2 here, I might as well just put it on the outside. Okay, so you see there, I'm just putting that factor on the outside, and then I have to multiply this by x minus 3. Okay, and of course this d now gets divided to the other side of the equation. All right. So let's continue going here. So I want to set this derivative to 0 because I'm looking for my critical points. So here we have x plus 3, and then here we have 2 times. So let's do this real carefully. We've got x cubed, okay, and here we have minus 3x squared. Then we have minus 6x squared. Okay, then we have, what am I left with here? Sorry, I lost track here. My phone's buzzing. So x cubed minus 3x squared minus 6x squared plus 18x. Okay. And then we have plus 6x minus 18. Okay, does that look good? Okay, do I care about this d in the denominator? No, why not?
I mean, you can just multiply both sides by d. And
Multiply both sides by d, or I have a fraction that's equal to 0, meaning that it's only the numerator that I'm interested in. Okay, so folks, I hope we were very careful in checking my algebra here, because one little error will cause issues solving this. So x plus 3 plus 2x cubed, so minus 6x squared. Actually, here I could have just, this would have been negative 3 minus 6 is negative 9, so this is just going to be times 2, minus 18x squared. This is 18 plus 6 is 24 times 2 plus 48 x, whoops, 48x, and then here 18 times 2 is 36, minus 36. All right. So let's keep going here. So we have 2x cubed. Looks like we have minus 18x squared. And then we have 1 plus 48 is 49 plus 49x. And then here we have 3 minus 36 is negative 33. Okay, so I'd just like everybody to take a look at that and make sure you're not seeing any calculation errors. Well, I just take, there's a few more people who came in, so I'm just going to take attendance there. Okay, looks good. Okay, Jacob, just, whoa, a whole bunch of new people came in. Give me just a second. Unfortunately, the free version that they provide for us doesn't allow me to keep track of who's here, so I have to do it by hand. All right, so I guess good news is we have an equation to solve. Bad news is it's a cubic, and so we're going to have to look for some zeros here. So what's the first thing I should be looking at, which I don't think is going to work, but what should I be taking a look at? Yeah, let's take a look if we can do some grouping. And I look here, well, if I take out a 2x, I'm going to have an x squared minus 9, and I will not have an x minus 9. Excuse me there. So what's the next option here? What's the only thing left for us here? Okay, so synthetic division, meaning first we have to use the factor theorem here. So this is where you have to make a decision. You know, if I was doing this, if I was, doing it as a homework assignment at this point here, I'd probably just stick it into Desmos and have, or, a function calculator to just figure out which one's going to work. So let's just test out some easy ones, okay? So again, I'm going to hope that it's not going to be a fraction. So I'm going to forget this 2 for now, but let's test, let's test 1. You've got, what do you have? You have 1 minus 18 is 2 minus 18, negative 16 plus 49. So let's get our calculator out. I don't want to do this in my head. Okay, so 2 minus 18 plus 49 minus 33. Okay, hey, look at that. Okay, I guess the textbook decided to be nice to us because x equals 1 makes this equal to 0. Okay, so we lucked out on this one here. So let me take my division here. So I've got 2, 18, whoops, negative 18, 49, and negative 33. And then what do we have? We said 1 works, so 2, so negative 18 plus 2 is negative 16. Again, please check my algebra here. So here we've got negative 16. So 49 minus 16 is going to be, no, looks like it's 33. Perfect. So it looks like this is going to work. And we have 0. I just check it just to be sure. Okay. Okay. Yeah, Kieran, I got that. Put you in. And so now what we have is this can be written as x minus 1, okay, times 2x squared minus 16x plus 33. All right. And so now we know that x is equal to 1 is one critical point. Whoops, x equal to 1 is one critical point. And now let's test to see if there's any others. So we have 16 plus or minus 16 squared minus 4 times, whoops, that's 33 there. 4 times 2 times 33, all over 4. And let's see what happens when we calculate the discriminant. Okay, so 16 squared minus 4 times 2 times 33, and we get a negative number. Okay, so does not exist. All right, so that means that our only critical point is at 1. Okay, so let's test our derivative. All right, so our only critical point, whoops, you can't see that, is at 1. And let's just test our cubic here. So again, what does this thing in the denominator represent? It just represents a distance between 2 points. And what do we know about a distance between 2 points? It's not necessarily constant, because we don't know what that distance is yet. Yes, exactly. It's positive. Okay, so meaning when I check my signs, I don't need to worry about calculating that distance, because whatever it is, it's positive. So I only need to work with the numerator. Now I'm going to work with this version of the numerator because it's already simplified. Okay, and this is where I tell myself, well, if this has no x-intercepts and has a positive leading coefficient, what can you tell me about all these values? Okay, so remember what we found. There's no x-intercepts and it has a positive leading coefficient. That tells me that whatever this parabola is, it's always bigger than or equal to 0. So I don't even need to stick any numbers into this whole big equation. I just have to look at the x minus 1. Okay, so if I put in 0, well, 0 minus 1 is negative, and if I put in 2, 2 minus 1 is positive. So what do we have? We have that throughout the whole domain, we have a local minimum at 1, but the function is continually decreasing up until 1 and then continually increasing beyond 1. So not only is this a local minimum, it's in fact an absolute minimum. All right. So before I write down an answer, I need to take a look at the question and see, because now I've spent so much time doing this, I forgot what the question was. So I look at the question, and here they're actually looking for the distance, the minimal distance. They're not looking for the x value, they're looking for the distance. So it's a good thing I went back to check my question. So now I just have to take my distance formula. So just so that you can see it, I'll put my answer up here. Okay, not necessarily the nicest thing if I was writing this out, but my distance is just given by, okay, the square root of, and I just have to input 1 into this equation. So what do we have? We have 1 plus 3 squared okay, plus 1 minus 3 squared minus 3, all squared. Okay, and let's simplify this here. So we have square root of, so this is going to be 4 squared is 16. Again, please keep track of my arithmetic here. So this is negative 2 squared, which is 4, minus 3 is 1 squared. So this is plus 1. So it looks like my answer is root 17 units. Okay, and that looks like our final answer. Okay, so just to recap, diagram, use this to create a model. In this case here, there was no restrictions on the x value. Okay, take the derivative and set the derivative to 0. In this case here, I chose to work with implicit differentiation, but you can sort of see that you would have gotten something very, very similar had you worked with more traditional differentiation. Okay, and from there, we determined only one critical point, and that critical point we justified to be an absolute minimum. Now again, on an evaluation, are you likely to have to use the factor theorem? Probably not, but in principle, certainly for a homework or assignment question, it's definitely up for grabs. You definitely need to, we assume that you know these things. All right, so questions on this whole one. So obviously it's one of the, it's not surprising that it's in the C part of the, or the extending part of the homework questions, not so much because it's a difficult question, but definitely the algebra was much more intense than what we did in class. Okay, any questions on this? Okay, so somebody's asking here, can you differentiate using, d equals the square root of this thing here? Yeah, that's perfectly reasonable. Okay, in this case here, you can use either scenario. Okay, so it doesn't matter which one you use. Anything else we want to ask about this one here? All right, so other questions. Okay, so the other two, 569, number 11. All right, so 569, number 11, and let's just take a quick look, make sure that's not on there somewhere. 569, number 11. Nope, perfect. There we go. So let's take a look at it here. 569, oops. So number 11. Okay, so two cyclists depart at the same time from a starting point along routes that make an angle of pi over 3 radians with each other. The first cyclist is traveling at 15 kilometers an hour, the second at 20 kilometers an hour. How fast are they moving apart after 2 hours? Okay, so it's a nice question because it's a little different from the ones that we had seen before. Okay, so I'm just going to move this aside so you can see the diagram that I'm going to draw. So this was page 569, number 11. Okay, so we have a particular point, okay, and they're moving, let's see, starting, oh, so they're both starting from this point, so that's good. Okay, so the first cyclist is traveling at 15 kilometers an hour, so they don't specify in what direction. The only thing that's important is the angle between them, okay? So how I draw this, so let's say I draw this first person here, and then the other person at pi over 3, they're traveling a little faster, so I'll make that a little longer. And so here, what we're looking for is how far apart, or how fast are the two cyclists moving apart after 2 hours, okay? So we want to know is how is this distance changing with respect to time, all right? So here, why did I allow myself to put in this specific value? You know, I always say you got to be careful. Exactly, it's a constant because they're moving in straight lines, so this pi over 3 stays constant, okay? However, what I don't want to bring in right away is this 2 hours, okay? Now, as we did before, you know, I'm going to try to set up a distance equation, except we don't have a right angle triangle. You know, you got to be careful, and it kind of looks as though it's right angled here, but maybe I should have made an effort to make it less, you know, look like less than a right angle. So I'm gonna be careful with that there, okay? But I've got this distance here, and who's gonna tell me how I can represent that distance? Yeah, even before I get to cosine law, I'm just going to come up. So I'm going to come up with a variable, but I can go a little further because I know that whatever this, you know, say d1 is, okay, is just going to be equal to the velocity times the time of travel. And I know that this is traveling at, so the first one was traveling at 15 kilometers an hour. So this one's going to be 15t. And then this one here, you know, my d2 is just going to be 20t, okay? And I think I had a good suggestion where somebody said, hey, why don't I use cosine law? You know, and if you remember correctly back from grade 10, Pythagoras is just a special case of the cosine law, all right? So now we have enough information to write a formula for this variable d in terms of time, okay? And so now we should be able to do that. In fact, we didn't even need to do this. I just realized here we're probably even making our lives more difficult than we need to, okay? Because if I call this, say, x and y, okay, it might actually just be easier to write d squared is equal to, okay, the sum of the squares of the two sides, so x squared, oh, I'm going to move this around, okay? Sorry, these windows are making it hard to see things here. There's just going to be x squared plus y squared minus 2xy times cosine of pi over 3, since that's a constant, okay? And what I realize here is I don't even need to write this in terms of time. I can solve this as a related rates problem because I know that the rate that this is changing is going to be related to the rates of the other two sides, all right? And so I don't actually have to write it in terms of time. I can do this even more easily than my original idea here, all right? So what is cos of pi over 3? Okay, so pi over 3 is the taller one, so it's just 1 over 2. Okay, so that makes life even better. Okay, so we've got d squared is equal to x squared plus y squared minus, okay, this is just equal to 1 over 2, so that's going to cancel out with the 2 there, minus x, y. Okay, and so now, what am I going to do to both sides of this equation? What rate am I interested in here? So I'm going to take a derivative here, but what derivative am I going to take from both sides is I'm going to take the derivative with respect to time of both sides, okay? So I'm going to take the derivative with respect to time of both sides. All right, so again, we kind of did this one before. It's just a straightforward chain rule. So this is going to be 2d times dd dt, okay? Equals 2x times x dx dt, okay, plus 2y times dy dt. And then here, what am I going to have to use now that I've got x multiplied by y. I'm going to have to use the product rule. Good. Okay. So derivative of the first, so dx dt, times the second function. Okay. Make sure I put brackets in front of here, plus the first function x times dy dt. Okay. And there we go. There's our related rates equation. Now, what do I know? What do I already know here? What did they give me straight out in this question? So let me bring up the question. Perhaps here, if we take a look and you see that what they gave me were those two velocities. Okay, so I'm going to write this down here. I know that this first velocity, let me move it a little so you can see, this first velocity x dx dt is just equal to 15, and dy dt is equal to 20. And what's the other piece of information that they give me? Is they give me that I'm interested in the 2-hour mark. So the time that I'm interested in is the 2-hour mark. All right. So let's see what we have here. Okay. So this is the thing I'm looking for. Okay. 2 times, wait a minute, I don't know what x is, or do I know what x is? Can somebody tell me what x is going to be equal to at the moment in time that I'm interested in? There you go, it's going to be equal to 30, because now that I've taken the derivatives, I can now input my specific information, but I'm not inputting it as a time value, I'm inputting it as a distance value, because this one that's traveling at 15 kilometers an hour for 2 hours, this is just equal to 30. And then dx dt is equal to 15. Okay? Plus, similarly here, y, what distance has it traveled after 2 hours? At 20 kilometers an hour, it's traveled 40 kilometers times dy dt, which is just 20. Okay? Then minus, and then very similarly here, dx dt is just 15. Y, we just figured out, was equal to 40. Oops, 40. And then minus x, which we realized was 30, times dy dt is equal to 20. Okay. And now this is the thing that I'm looking for. So I have to divide by 2d. But how am I going to determine what d is equal to? Can somebody tell me how I'm going to determine what this d is equal to? Exactly, because now I have exact distances. I know that this is going to be, oh, sorry, this was 40. This was 30. This is still pi over 3. And now I can calculate that particular d value. I'm missing a 20. So where am I missing the 20 here? Ah, here. Thank you very much. I think this is what you mean. This should be not 2, but 20. Good catch on that one. Thank you. All right. So now I can just use cosine law here. So d is equal to the square root of 40 squared plus 30 squared minus 2 times 40 times 30 times, well, we already know that that's a half. We calculated cos of pi over 3 before. So what is this equal to? Let's just take our trusty calculator and calculate. Okay, 40 squared plus 30 squared minus the 2 and the 1/2 cancel out. So minus 40 times 30, and that's equal to 1300. Okay, so square root of 1300. And now we have all the information we need to determine the derivative of d with respect to time. So again, check if you can take a look at my calculator, make sure I don't miss anything. So 2 times 30 times 15, okay, plus 2 times 40 times 20, minus 15 times 40, minus 30 times 20, and then divided by, actually this would work out pretty nicely, looks like, okay, divided by 2 times square root of 1300. Okay, so that looks to be 18, approximately 18, and what was this? This was in, I'm going to assume kilometers per hour. Yeah, kilometers per hour, thank you. All right. Okay, so essentially what they're telling us is what we're seeing is that at that moment in time, the distance between them is increasing at a rate of 18 kilometers per hour. All right, so obviously this one here, you notice that once we had the equation, you know, there's no one particular part of this that's necessarily difficult. There's just a lot of parts, okay? Because you have to be careful of taking your derivative, making sure you're applying the product rule, making sure you're not forgetting, you know, your brackets, you know, that would have caused a problem by not distributing the negative, and then realizing that at t equals 2, you were able to calculate the x value, the y value, and the d value with a bit of work, okay? So before I go on to the next one, any questions on this one here? Okay. Okay, so I'll move on to, what was that one? 570, number 16. All right, give me just a second. I need more paper here. Okay, so again, last call on questions here. No, okay. Okay, so 570, number 16. So let's find 570. Oh, this is the same thing here. So here it says a conical paper cup with a radius of 5 centimeters and a height of 15 centimeters is leaking at a rate of 2 cubic centimeters per minute. At what rate is the water level decreasing when the water is 3 centimeters deep? Okay, and this should be similar. I think it was a cone. This should be similar to one of the questions from the worksheet, one of the ones that I didn't take up, okay? And you would imagine that this would be an important type of question. Let's say you've got some sort of large container that gets refilled regularly, and then all of a sudden you've got some leak that appears. You need to know how that's affecting the rate at which the water level is changing, okay? So this is page 570. Number 16. Okay. Yeah, we'll see how it goes there for number 15. Okay, so as usual, let's draw my, let's draw a diagram here. So I've got this cone. Actually, I probably should have just drawn a cross section of it. Okay, that would have been a little easier. All right. And it tells me that the radius is 5. And then the height is, what is it? Height is 15. Okay. So those things are constant because the paper cup is the paper cup. It's not going to change. But what's happening here is water is leaking out of the paper cup at, 2 cubic centimeters per minute. All right. And so here, there's some water in the cup. I don't want to assume it's the top. Remember what I do when I draw my diagram, I want to draw a general moment in time. So there's some water here at some point in time, okay? Do I know what the radius of this sort of cone inside the cone? So this is the cone of water inside this larger cone. Well, I don't know what that radius is at that moment in time, okay? Now, yeah, we'll get to that in a second, okay? Now notice here, they tell us when the water is 3 centimeters deep, but that's at the one particular moment in time, all right? So what I wanna do is I wanna set up this, and I'll just call this R for radius, okay? And I guess I'll use H for height. And I think I see a couple of people here already seeing that even though I've got these right angle triangles, Pythagoras is of no use to me because I don't know anything about this hypotenuse, and I'm not interested in this hypotenuse at all right? So what I want to do is I want to find a way to relate these two equations, all right? So let's take a look here. So here it says that what rate is the water? So let's write out our similar triangles thing here. Okay, so I've got this side here is corresponding to that side there. So R over 5 is to H over 15. Okay, so everybody good with what I did here? Okay. Let me know if you have a question on what I did. So I just use these similar triangles, and the ratio of corresponding sides is equal regardless. As long as the sides are corresponding, the ratio is going to be the same. All right, no questions? So the question is do I want to write R in terms of H or H in terms of R? So look at the question here and ask yourself, what is it that I'm actually looking for? Okay. So I'm seeing a bit of discussion. So what are they asked? Let's take a look at what they're asking for. They're saying at what rate is the water level decreasing? That means I would like H to still be in the equation, okay? Because look at the information they've given me. They've given me a water level, they've given me an H value, and I'm looking for the rate of the H value, okay? So I agree, whoever said, you know, those of you that said R in terms of H, I think that's the way to go because H is what I want left in my equation, all right? So what I'm gonna do here is I'm gonna write R in terms of H, even though it's the more annoying one because it means I'm gonna have a fraction, okay? So this will just be H over 3 because 5 over 15 is going to be H over 3. But now when I write my relationship, okay, between volume, because that's the rate that I'm given, and the rate that I'm looking for is the height, all right? So when I write my equation, V equals, and again, I don't necessarily expect you to remember these things, but you can easily look them up, is just 1/3 pi r squared h. So the volume of a cone is just 1/3 the volume of the cylinder with the same volume of the cylinder with the same height and radius, all right? But now in order to make this more user-friendly here, wherever I see an r, I'm going to replace it by h over 3, all right? So let's just keep simplifying here. So 1/3 pi times h squared over 9 times h, and so v is equal to, well, it looks like in the numerator I have pi h cubed over 3 times 9 is 27, okay? So here it says, can't we use the relationship R over H equals, well, it's the same thing. Okay, so Samya, you see, the way I write it, whether I take the two sides from the smaller triangle and compare it to the two sides in the larger triangle, or I compare corresponding sides, it gives you the exact same relationship. What you have, R over H, is just like dividing the H here and multiplying the 5 there. So whichever way you write it, doesn't matter. In the end, you would come up with the exact same relationship. Is that okay? Okay, Samya, looks like you just saw your error, no problem. Okay, so what do we have now is I have a relationship between the volume of water in the cone and the height of the water in the cone, okay? But what I want to do is I want a relationship between their rates of change to create a related rates problem. So I'm just going to take, take ddt of both sides. Okay, so this time here, I'm going to allow myself to use prime notation just to make the writing of it a little easier. So we have v prime equal to pi over 27 is just a constant. And so now, again, I'm going to have to use the chain rule because remember, I'm taking the derivative with respect to t. So the derivative of the outside function is just going to be 3h squared times the derivative of the inside function, so the derivative of h with respect to time is just h prime. And this now is my related rates equation. Okay, because I now have a relationship between the derivative of velocity, volume with respect to time, and the derivative of height with respect to time. But this is where now that I've taken the derivative, I can start inputting the things that I know. Now, be very careful here. They give me the rate of change of the volume with respect to time. But what do we have to keep in mind here? That's going to make a difference in our answer. Who wants to tell me how I'm going to input that rate of change of volume with respect to time? Okay. Exactly. I need to input negative because what's happening here, it's leaking water, meaning the amount of water is decreasing with respect to time. So very important to be putting in -2. All right. And on the other side here, well, let's cancel those out. So I'm left with pi over 9. Okay. They told me at that particular moment in time, the height is 3 centimeters. So that's just going to be 3 squared, which is going to cancel out with the 9, and then h prime. So in fact, the only thing I'm left with is h prime is equal to -2 over pi. Okay, and since this is an application question, we're going to approximate that. So we have -2 divided by pi, and it's about -0.64. So -0.64, and here it's centimeters per minute. Okay, because the length measurements are given in centimeters and the time measurements are given in minutes. All right. So this tells us that as this water is leaking out, how quickly the height is changing with respect to time. Okay. So now we've seen, I think this is now the third question that's come up, at least. There might be other homework questions where this has come up, but this is at least the third now that I've taken up where, in fact, the fourth now that I think of it. The third that I can think of where we're using similar triangles to help us solve an equation. All right. Any questions on this one here before I move on to maybe we'll make it the last one? Okay. So again, folks, I really want to reiterate how, this is one of the most important applications of differential calculus there is, because this type of thing you can see coming up in, this comes up in chemistry and biology, in engineering, in physics all the time, in economics all the time. If you know the rate at which one measure is changing, can you use that to help you determine how another measure is changing, and almost always with respect to time. All right, so we're being asked for when do we use marginal cost and marginal revenue? So again, that's used in economics when they're trying to figure out sort of the best, the best number of items that you're trying to sell in order to maximize your profit. Okay. So I think I explained that in a previous video on marginal cost and revenue. So if you want to maybe take a look at that, otherwise send me an email and I'll send you a bit of an explanation on that. Okay. If you look at the intro video to that lesson, you'll see that I explain marginal cost and revenue. Okay, so let's take a look at number 15 here. The trunk of a tree is approximately cylindrical in shape and has a diameter of 1 meter when the height of the tree is 15 meters. If the radius is increasing at 0.003 meters per year and the height is increasing at 0.4 meters per year, determine the rate of increase of the volume of the trunk in this moment. Now this is interesting because they're looking for the rate at which the volume increases. Do you notice something a little interesting about the information that's given? That's different from at least any of the other ones that I've taken up. There you go. You're given two rates. All right. And let's see how this might come into play. So let's draw ourselves a picture because it's always kind of good to get ourselves settled. Okay. So we're going to assume that this tree trunk is a cylinder. Okay. I don't want to input these values here of 1 meter and 15 meters because this is not a constant value. This is at one particular moment in time that the dimensions have these numerical values. Okay, but I do know that in order to work with the volume of the trunk, I'm going to need the radius and I'm going to need the height. Okay, and they give me the rates. So if I want to try to work with the volume of this tree trunk, well, we know it's pi r squared h, but here we've got two variables. What do they not give me though? Can you see something that they do not give me? Something that I'm not able to do in this question that I've been able to do in a lot of the other questions when I have two variables. Anybody? There you go. Doesn't look like we can write one in terms of the other. They don't give us any constraints. In that last problem, they gave us the constraint that this water was living in a cone of radius 5 and height 15. Those were given constants. Here, there's no information that allows us to write one of these in terms of the other, or to write both of these in terms of a third variable. So I'm still looking for how this is changing with respect to time. What should I do? Should I just stop, or is there another option here? What might I try? No Desmos. Whoever said stop the Desmos thing. There you go. Let's just still take the derivative of both sides. And see what happens. Okay. Maybe it won't work, but maybe it will. So let me take the derivative with respect to time. So again, I'm going to use prime notation, v prime, but this is where a couple of people suggested here, well, wait a minute. Pi is just a constant. I can use the product rule on these two measures that are being multiplied. And hey, they did give us two rates. So out of this is going to come a dr dt and a dh dt, both of which were given. Okay, so this is a scenario where you're going to be working with the two variables. All right, So let's use our product rule here. So remember, we're taking the derivative with respect to time. So I'm going to have to use the chain rule here. So derivative of the outside function is 2r times dr dt, so r prime, times the second function, plus the first function, times the derivative of the second function. That's just going to be dh dt. Okay? And when you look at what you have in this equation, in this related rates equation, is you know the two rates of change, and they give you a specific r value and a specific h value for the moment in time that they're interested in. Okay? So this is where now v prime for the moment in time that we're interested in, okay, is just equal to pi times 2 times, well, the radius is equal to, okay, got to be careful here. You don't want to get taken in. What is the radius? Very careful here. There you go. Make sure you're careful. What they're giving you is the diameter, yet what you need to input is the radius. So this is going to be 0.5 times r prime is 0.003 times h, which is 15. Okay. And then plus r squared, so that's 0.5 squared times h prime, which is 0.4. Okay, so if we can just take a quick look here, make sure I wrote everything correctly. Can you just all take a quick look before I put this in the calculator? 2r prime h plus r squared h prime. Okay, well, it looks good to me. Nobody's telling me anything. I'll assume it's good. And so now let's stick this into our calculator here. Okay, so 2 times 0.5 is just 1, so 0.003 times 15 plus 0.5 squared times 0.4, and then all that times pi, and looks like we've got 0.46. Okay, and this is going to be cubic meters. Okay, and I'm going to guess that this is per year. Cubic meters per year, yeah. Okay. And I see someone saying that they found it, there's a different answer given in the back of the book. Yeah, okay. So it could be the, I'll try to put that out here. So for this one here, looks like there's an answer in the book unless, so that's it. They didn't multiply by pi. So it's funny how very often you can almost guess at what the mistake they made is, okay? So definitely we need the pi because it's a constant. It doesn't disappear when you take the derivative. So they might have just forgotten it in taking this derivative. All right. So again, this is a nice problem because, sorry, this is number, was this 15? A nice little problem because it gives us a different view that sometimes, oh, okay, so I'm assuming 0.145 pi is equal to that there, okay? So an interesting one because here we were able to still work with the two different variables, and we could just use our product rule in this case here, okay? So I think I'm going to say that for now, let's end this for, I just have a couple of questions I do want to ask you, a couple of things I want to let you know about. I'm just going to stop the recording here.